So today's presentation is the results of the students' work that has been partially funded by Polar Knowledge Canada and the Northern Science Training Program. So I am going to get started with the first speaker. Nothing like taking the present. So here we are. First of all, we have Tessa Baker, who is from the Department of Ecosystem and Public Health. Come on up. So you can hold this and pin this, whatever you want to do. Or you can just gather a little piece of fabric.
All right. So I'm from the Faculty of Veterinary Medicine, and I'm going to tell you about my master's project. So my project was based in the Co2 settlement area of the Northwest Territories, which is a Dene, First Nation, and Métis land claim area in the central Northwest Territories, made up of 5 communities: Colville Lake, Fort Good Hope, Norman Wells, Delaney, and Toledo. The number of people living in this region in 2016 was just over 2,500, and the communities varied in size from 160 to 803 people. The largest community here is socioeconomically and demographically different than the other 4 communities. You can see they have very high average annual incomes. Their economy is largely dependent on the oil and gas industry, and they attract people from across Canada for work, and therefore their population is more than 60% non-Indigenous. The remaining 4 communities have, compared to the Northwest Territories average, higher unemployment rates, lower personal average annual incomes, and a greater percent of families living in core housing need. And their populations are predominantly Dene, First Nation, and Métis. They also have high cost of living in the area, and many people in these 4 communities still practice traditional activities like hunting, fishing, and trapping to both supplement their income and also as part of their culture. So like many communities in the north, these 5 communities are very remote, only accessible by winter road for a few months of the year or by air year-round. 3 of the communities are on the Mackenzie River and are also accessible by barge in the summer. The nearest vet clinic to these communities is, the communities are up here, is in Yellowknife. And on this map, the red lines are permanent year-round roads, and the blue dotted lines are winter roads. So it just gives you an idea of how isolated they are from services further south. So veterinary clinics actually became available annually in these communities in 2008 after community members raised concerns about dogs to vets that were in their communities doing wildlife disease monitoring. And they talked about how dogs would become sick and they would have no way of getting them out of the community to get help for them. And dogs were constantly interacting with wildlife with the risk for transmission of rabies virus, which is endemic in Arctic fox. Oops, sorry. The clinics began after people from the Faculty of Vet Med did a assessment of what the acceptance of and needs for vet services would be in the region. And this assessment just highlighted a number of animal welfare and human health concerns. So people described there being way too many dogs in the communities. Kids commonly described being chased and bitten, and interactions with wildlife were really common. There were low rabies vaccination rates in dogs and deworming of dogs, which is important because there's parasites that dogs can transmit to people. And sterilization of dogs was also very uncommon. Also, more than 50% of the dogs that were seen at the first clinics in 2008 were considered to be too thin. So since then, clinics have run every February, offering services of vaccination, deworming, sterilization, surgery, and also education about those diseases that are transmissible from animals to people. And because the clinics run in the school, we also do outreach in the classroom, including dog bite prevention sessions. So because it's really uncommon for subsidized veterinary programs to run for so long in one area, we're going into year 12. And also because it's really uncommon for programs to be evaluated for their progress and their value, the purpose of my master's project was to evaluate the program to understand what, if any, impacts the program might have had over the 11 years on dog health and welfare, and also community concerns about dogs. And I focused mostly on the 4 smaller communities. So my research questions were, does annual access to vet services improve dog population health and welfare? Does it decrease community concerns about dogs? And given that we feel we give consistent service delivery in each community, do these changes occur similarly across all communities? So after gaining approval from the communities for my proposal, I went in the summer of 2017 to do a dog census and a household questionnaire. And then I did an analysis of the 11 years of dog medical records. And finally, shared all the results back with the communities for their feedback. So the dog census and the questionnaires were done together in the summer of 2017. And the dog census was used as a denominator of the total number of dogs in the communities to understand better the reach of the program and the vaccination coverage achieved. And I used sort of 3 approaches to try to get a census. So visually counting dogs outside of households and marking them on the household on a community map. I used completed community questionnaires to give me an indication of how many dogs were in a household. And then finally, I talked to locals with knowledge of dogs, such as bylaw officers and teachers, for the households that I wasn't sure of. They helped me with those ones. The household questionnaire was done to understand husbandry practices around dogs, attitudes towards dogs and vet services, and experiences with dogs. And it was very similar to the one that was used in 2008 in that initial assessment. And I went door to door with the questionnaire, trying to reach as many people as possible, both dog owners and non-dog owners. After the data was entered into Excel, I did both descriptive and inferential statistics, looking for differences between 2008 and 2017 responses, and also differences between communities in 2017. And finally, there were 2 open-ended questions that I did thematic content analysis, basically looking for the major themes that came out of the responses to those questions, and then the frequency of those themes. The last part was doing the 11-year medical record chart review. So there was more than 2,000 records on more than 1,600 dogs, and I was looking for changes in dog health and welfare measures, including age, sex, breed, body condition, spay, neuter status, and vaccination and deworming history. Dogs and owners were given unique ID numbers so that I could track them over time. And I did logistic regression and linear regression analysis. And I broke the 11-year time interval into 4 time periods. And then, like I said, the final part was to share those results this last February at the veterinary clinics through a community feast in each community, in order to present the results back, but also to have further discussion around dogs and gain community feedback on our results and our interpretation. Summary reports and posters were shared with community councils and other stakeholders like schools. And most recently, manuscript summaries have been shared with community councils for approval. So I'm just going to share some of the results because there were a lot. So overall, I was able to complete 114 questionnaires, which represented 21% of households in the 4 communities, and 48% of those households own dogs. 69% of the households that responded were dog owners themselves. Given the concurrent dog census, I know that the questionnaires represented 51% of the dogs that were in the communities at the time, and that ranged between 30 and 70% depending on the community, and so that gives us some good dog husbandry information for each community. More than, or nearly 1/3 of respondents were female, and nearly half of them were between the ages of 40 and 59, and the average number of dogs per household was 1.6. The dog census findings made it obvious that there was a variability between the number of dogs that lived in each of the communities, varying from 40 to 89, and that meant obviously that the percent of dog-owning households also varied from 18 to 66. When we look at the number of dogs and owners seen at the clinics over time, we see a pretty sharp increase in the first few years and then an almost plateauing, suggesting that we might have reached saturation for need of services. When we did logistic regression on on repeat dogs, we also found that we were much more likely to see a repeat dog as time went on. When we look at the sex ratio of dogs described in the questionnaires, we see a male skewed sex ratio and no significant change between 2008 and 2017. And this was corroborated by the medical record analysis, where we also didn't see a change in the sex ratio over time, with it remaining consistently skewed towards male dogs. The spay and neuter status was another piece that we looked at. As one would imagine, as services become available, you would expect to see more sterilized dogs in the communities, and that's what we saw in the questionnaires. This was also corroborated by the medical record analysis, where we saw an increase in the likelihood of seeing a sterilized dog over time. This, however, did vary by sex, so we were much more likely to see a spayed female dog than a neutered male dog, such that we were 9.2 times more likely to see a spayed female than a neutered male dog in clinic. And this suggests that that there was much more acceptance for spaying female dogs than neutering male dogs. Oh, sorry, I just wanted to say one more thing. This also varied by community. In one community, literally only 2 male dogs had ever been neutered in that community. So there were also community differences in spay and neuter status. Dog age also increased. So in the questionnaires, the dogs that were described in 2017, the median age was 1 year older than in 2008. And again, this was corroborated by our medical record analysis, where we found that the age of dogs increased over time. And this suggests that dogs are living longer and that there are maybe fewer puppies in the communities. When we looked at the body condition of dogs at the last clinics in February 2008, 70% of dogs were in ideal body condition compared to 38% in 2008, and none of the dogs in 2018 were emaciated. When we did the medical record analysis, we also found that our likelihood of seeing a dog in ideal body condition compared to one that was too thin also increased as time went on. And although this relationship is not significant, so we don't see an increase in likelihood of seeing an overweight dog compared to an ideal dog in clinic, we do worry that this might be a trend that is also common down here, and obviously an unintended consequence of the program related to diet and also related to an increase in sterilization of dogs. But overall, dogs are in better body condition. When we looked at vaccines, again in 2017 questionnaires, many more dogs were described as vaccinated for rabies virus and against the other dog viruses that we vaccinate them for, and also had been recently dewormed. Again, this was corroborated by the medical record analysis, where we found that there was increased likelihood of dogs being vaccinated and dewormed over time. This is really important to public health because high rates of rabies vaccination is important in a region where rabies is endemic in wildlife, and also regular deworming is important when there are parasites that are transmissible from dogs to people. People were also asked about the purpose of their dogs, and in 2017, many more people described their dogs as companions compared to in 2008, where people were almost unsure about how to describe them based on the list we gave them and almost picked companion as a default. And also, in 2017, 90% of people strongly agreed with the statement, "I feel that my dog is part of my family," and no one disagreed. They were also asked about what their dog eats every day. And in 2017, 57% of dog owners fed their dog store-bought food compared to 38% in 2008. And when we look at individual communities in 2017, this increase in store-bought food was true in communities A, B, and D. But in community C, table scraps and fish were still fed more commonly. So in order to understand a little bit about the attitude towards dogs, we did a similar process to what they did with the questionnaires in 2008. We looked at 4 Likert rank questions. So I like dogs very much. My dog is generally happy. My dog is healthy. And I'm afraid of most dogs. And analyzed it and gave an overall score, positive versus negative, to describe the overall attitude towards dogs. And we found that in 2017, 77% of respondents had an overall positive attitude towards dogs compared to 62% in 2008. We also looked at four other questions that were asked to all questionnaire respondents, regardless of whether or not they had dogs, to look for differences again between 2008 and 2017 responses. And those questions were, there are too many dogs in my community, I like dogs very much, I'm afraid of most dogs, and when a dog bites someone, it should be killed. And we found that only one of those questions was answered significantly differently in 2017, and that question was, there are too many dogs in my community, and fewer people agreed and more people disagreed with that statement in 2017. So the final part was the thematic content analysis, and so one of those 2 questions was, does your community have issues with dogs? And 2 out of 4 of the communities strongly felt that they did. And the main themes that came out of the responses to that question were loose dogs, people as the problem, and how loose dogs are dealt with loose dogs being the predominant theme across all communities. And people described loose dogs as nuisances or beings that they feared, or just specified to them as like strays or free-roaming dogs. The people who said that they felt people were the problem, they felt that people needed to take responsibility for their dog, take care of them better, tie them up more often. They weren't blaming the dogs themselves. And finally, the how loose dogs are dealt with was most specific to one community where they felt that the bylaw officer was too quick to shoot loose dogs. The second open-ended question was, have issues with dogs changed over the last 10 years? And there was a real mix between communities of whether they felt yes or no change. And there were 5 themes that came out of that question. So physical changes seen by community members, so fewer loose dogs, fewer puppies around town, increased access to options to deal with problem or loose dogs. So people described having access to vet care as being very helpful because there was more dogs being spayed and neutered. Also having an opportunity to send unwanted dogs to the SPCA and Yellowknife was also very beneficial to them. Changes in the welfare and value of dogs. People felt that overall dogs seemed to be treated better and that there were fewer dog shoot days. And then less fear of dogs, so in particular elders described being less fearful of walking around town. And then bylaw enforcement was described in 2 communities as being a positive, something positive that was benefiting the community. Physical changes seen by people was the predominant theme across all communities. So to sum up, the program uptake has increased and may have plateaued or been saturated. Dogs are more likely to be sterilized. Dogs are living longer. Dogs are in better body condition. Dogs are more likely to be vaccinated. Dogs are more commonly described as a companion. Dogs are more commonly fed store-bought food. And some communities feel more positively about dogs and dog issues. So there are many lessons learned from this evaluation, but I think I'll just highlight one of them, and that was the community differences that we noticed in both uptake and how people describe dogs and issues with dogs in their communities. And we feel that it's really important for us to think about those differences and acknowledge them so that the program can be successful long-term in each community. And this research, given that it's run long-term in one area, adds to the research on subsidized veterinary program evaluations, but in particular in Indigenous communities. And it shows what can happen if you commit long-term to one area instead of helicoptering in and then moving on to somewhere else. And it could be used, the results could be used by communities in the development of their own dog management plans, but also could help guide programs in other underserved communities that don't yet have services. And I have lots of sponsors, including NSTP support to thank, and lots of community members who also helped out. Thanks.
So does anyone have any questions? Yes.
I'm curious, when
we just shared. Yeah, we just.
Curious as to how they would acknowledge the differences.
Yeah, we just shared the individual community results with them. We didn't want to make them feel like that there was some kind of level they were trying to achieve, or like, do you know what I mean? Yeah, and it was.
I would have been surprised if you said yes.
Yeah, and they're also different, so they all sort of manage things slightly different. So what works somewhere might not work for them. So it didn't really seem relevant to do it that way.
Great.
I was going to ask the same question,
Yeah.
sorry, but that was like a really good question. But what kind of response did you get from the communities if you like, didn't share between the communities? Were people interested in the feedback? Did they like want to hear like more about what you were doing? Like, how did that go?
It really depended on the community.
Yeah.
We had a feast because we felt that if there was food, more people would come, and that was true. But yeah, like lots of people were very like interested and asked great questions. In one community, it stirred up a lot of that we didn't realize was there, but that like kind of internal community conflict between dogs and dog issues, and that was like really uncomfortable for us because we're like, oh God, what do we do? You know, we've like opened this can of worms. But again, it's like interesting to see how complex it is when you live in a community of 500 people. Like what people do affects you, and yeah. So it was mixed, but it was worth it afterwards. Yeah.
Yeah. One of your first slides, I thought I saw, and I might be wrong, that you only were able to interview 25% of the households.
Yeah.
Is that correct?
Yeah, 21, I think. Yeah.
So, first of all, how come only that number? And I guess, do you think that affects your results?
And again, that was like the 4 communities overall, and it varied between like 70% and like I think 18%. So there was one community I struggled really, really hard to get anyone to open the door when I knocked. And I would go around to businesses, and I got a few done that way. It was just that community was really difficult, so it got pretty bad coverage of that community. So for sure, those results, you know, you want to interpret in light of the fact that I probably only spoke to people who were interested in speaking to me. But I was told, and I guess because you're always on a timeline and you're trying to make things sort of efficient, but within the context that you're working, I was told that like door to door might be difficult because when Census Canada comes around, they're very, very aggressive, I guess, with people. And so people are a little bit like hesitant to open the door and things like that. So I wondered if that would influence it, but mostly just one community that was not well covered. Mm-hmm.
Thanks. Thank you. It was great. Okay. So next we have Andrew Clark. You're from the Department of Geography. Between, because Tessa, we lost her sometimes when she turned.
Sure. How's that? I don't know. Good? Cool. All right, should I get going? Yeah. I'll be changing gears a bit. As Patty said, I am a second-year PhD student with Brian Moorman and Chris Hugenholtz with the Department of Geography. Today, so I'm still kind of working through my results and processing data, so I won't really be focusing on that today. I'll be focusing on context and my objectives. So my research is focusing on Arctic coastal retreat in the context of climate change, and then how nearshore permafrost plays into that process. Oh, it does jump. So, being in Calgary, the landlocked city that it is, there's not exactly a ton of coastal research going on here. So I thought it would be important just to highlight why some of the issues that are affecting coastal communities because of climate change. So when we think of climate change affecting coastal communities, the number one thing is kind of sea level rise. How much sea level rise is going to depend on where you are in the world, but when you add that to there being more energy in the system, so there's going to be more frequent storms and more intense storms, there's expected to be kind of worsening effects of coastal erosion or other things like ocean acidification, things like that. But the reason I'm interested in coasts and studying coasts is because I come from one of these highly sensitive areas in Canada. I'm from Prince Edward Island, the smallest province in Canada. We are vulnerable or sensitive because of sea level rise. We're seeing more and more storms, and they're more intense. But also our sediment is sand and sandstone, so it's really susceptible to erosion, so wearing away from wave action. And we're also seeing that we're losing winter ice cover, which protects the coast from storms that come from the north in the wintertime. And the coasts are really important to PEI because it's kind of the main economic driver of our province. There's tourism, fisheries, aquaculture, and there's lots of infrastructure along the coast. So it's a big deal for us. But I'm here today to talk about the Arctic. So my research is focusing on in the area, the Mackenzie Delta area in the Beaufort Sea, but specifically in and around the hamlet of, this is bad, I'm sorry, Tuktoyaktuk in Northwest Territories. So up there is kind of the same story. There's sea level rise, increased storm events, increased frequency. The sediment up there is unlithified, so it's soft, it's susceptible to wave action. But what's unique about the Arctic is that it's underlain by permafrost. So not only is there mechanical erosion, there's thermal erosion as well. And we know that there's disproportionate warming going on in the Arctic. So when you couple these two things together, we're expecting to see increased impacts along along Arctic coasts. What is also happening is there's a reduction in sea ice cover. So not only is this affecting or contributing to the feedback mechanism where instead of the solar radiation being reflected from the white ice, it's being absorbed by the dark ocean, thus increasing the temperature of the water. This increased temperature of the water would then have an effect on the permafrost. What is also happening in this area is that the sea ice is decreasing in the direction of the prevailing wind in the Western Canadian Arctic. And this causes an increase in fetch. And what I mean by fetch is the distance over which water or wind blows over water. So when the fetch is bigger or longer, more energy can get transferred from the wind into the waves, thus causing more wave action along the coast, worsening erosion and flooding. So when we talk about coastal impacts, it's often very localized. So it really only matters to the people that live there or the people that fish there or whatever. But Arctic coastal retreat actually has a global significance, and that's because there is organic matter trapped in the permafrost. And when this gets released through erosion, this organic matter will eventually or can transform into carbon dioxide and methane, making its way into the atmosphere. So, and this is seen to be a major source of greenhouse gases that hasn't been accounted for in any of the climate models to date. So this is a really hot topic of research for people studying Arctic coasts. We want to try to quantify what this contribution is to global greenhouse gases, gas levels. So when we look at just to highlight some of the major sediment sources along the Arctic coast, there's two types of coastal types that contribute major sources of sediment. It's these retrogressive thaw slumps, These and block failures. Retrogressive thaw slumps occur when there's excess ice in the permafrost. When this melts out, there's a loss of cohesion between the sediment particles, and basically it just turns into a liquid and flows out into the near shore. And then we also have these block failures, and how these occur is the wave action undercuts the cliff, creating a notch. When this notch gets deep enough, the force of gravity takes over, and then these big blocks of earth fall into the ocean. And so when you'll often hear really high rates of erosion in the Arctic, being on the order of 10 to 20 meters sometimes, and it's kind of this process that they'd be talking about. So I'm going to just step into the near shore for a minute and talk about what's happening under the subsurface and underneath the ocean, or in the near shore. So we have a kind of a profile of a block failure, and so there's ice under here, and when we have one of these block failure events, this ice is no longer insulated by ground. It's now there's now water over top, so that changes the thermal regime. And then the significance of that is that when this ice melts out, instead of having a shallow bottom fast or a shallow near shore, the profile deepens. What this means is that the waves can be bigger, and then that has more of an impact on the coast. So it's kind of another feedback mechanism, where these waves are bigger, and then they're faster to create deep notches. So this process will continue and create more and more block failure events. But if we kind of go back up to the surface, and how people have been trying to quantify, how people generally quantify coastal change is there's this metric, it's the coastline. Often what people will use is, for the definition of it, is the land-water interface. And we can see kind of from this diagram above that these coastal systems are a lot more complex, especially these retrogressive thaw slumps. So what can happen is that you can have your coastline, the land-water interface, you can have multi-year data, and that line doesn't really change. But when you look at at what's actually happening, there's major retreat of the head wall and tons of sediment flowing into the ocean, but it's not being accounted for by just this line. So there's kind of this push to do things in 3D and calculate change in terms of volume instead of just this single coastal metric. So we look to, oh my God, I'm sorry. When we think about coastal change generally, but even in the Arctic, we look to use satellite imagery. But I think everybody knows you need to consider resolution when you're doing this. So for example, this Landsat image is 30-meter resolution. You can't really see any defined features. You might be able to extract a land-water interface from this, but again, when you do that delineation, it's not very accurate because your pixels are 30 meters by 30 meters. So when you increase the resolution to this, for example, a 10-meter spot image, you can start to see that this is an area that it might have retrogressive thaw slumps on it, but you still can't really define them accurately. You might be able to improve your definition of that land-water interface, but it's really once we get into high-resolution data like this worldview meter resolution that you can start to see that this is, you can sort of see where the active flow is, where the vegetation is. You can see the head wall quite definitively, and other coastal metrics. But even still, when you're using this and you zoom in, it'll still get fairly pixelated because they are meter and a half or so size pixels. So there's some inaccuracy in doing that. The other disadvantage is that you're just getting a 2D image of this. There's no elevation. So this is why we kind of turn to and are moving towards, at least on the small scale, using UAVs. How UAVs will work is you take a series of images, overlapping images, you run it through some software that uses the structure for motion algorithm, and then what this spits out is a really high resolution orthomosaic, they call it, on the order of centimeters. But what's also advantageous to this is you get a digital surface model. So you get elevation at the same time that's of equal resolution. So when you zoom in on this, you can really see defined features. This is just the top of the head wall, but you can see like there's almost no pixelation with this. So this kind of brings me to my objectives. The first one being so the common method for calculating change is for somebody to go in and manually digitize any of these metrics. That, of course, is time-consuming, error-ridden. So what I'm working on is using a different approach of classification known as geographic object-based image analysis, which I'll speak to about a little bit more in the next slide. But what this allows you to do is automatically or systematically extract different coastal metrics from this high-resolution imagery. So then what we would do with this is get multi-year data and then compare these data sets to get a volume. So when you're with Geobia, or object-based image analysis, you create a rule set, which you apply to multi-year data. So then you use the elevation models and these metrics to quantify how these different parameters and metrics are changing over time. And then we don't want to just focus on these small areas. We want to be able to quantify a change over a large area. That's kind of the goal, to quantify the contribution across the whole Arctic to greenhouse gas levels. So the idea would be to take these rule sets and scale it up to the worldview data, for example, and then couple that with an Arctic DEM to estimate volume change over a larger area. And then, this thing is terrible. So when we're talking about volume change, especially in the Arctic, we need to consider massive ice underneath, because that's a major, it's a lot of volume. So we are going to use GPR, ground penetrating radar, to map the massive ice in these areas that we study, and then use single beam, probably sonar, to map the near shore so we can understand how these changes are going to potentially impact Arctic coastal retreat in the future. So for how Geobia works is it kind of mimics how the human brain or eye interprets images by seeing patterns and differences in colors. So when we just look at this, we can see these differences. Similarly, when you go to the aerial view, you can see exactly where the cliff is. You can see the different colors. You can see where the vegetation is that might indicate that it's a stable flow, or this white area that's flowing out of some massive ice. So how Geobia works is you create a segmentation, which instead of just going pixel by pixel based on the spectral properties of that pixel, it takes into account what's around it and creates these homogeneous polygons that you can then further refine through rules. So you can take elevation into account, so to help you better identify where the cliff top edge is or where the toe of the cliff is, for example. Or you can use vegetation indexes to kind of separate the image into these different areas. So you make these refinements. There's quite a bit of trial and error. But what you would then do is, after you have your kind of classification scheme set, you would then merge these polygons into a classification. So we would anticipate having maybe 4 different classes here for vegetation or tundra, moving into cliff, then beach, then water. And if you look close, you can really see that it's an almost exact definition of these features. For example, the cliff, the tundra, is exactly defined. You would never be able to do this manually to this accuracy. So I think I will just try to put this, I guess, in a little bit more context and how this is contributing to Arctic coastal research. And I really think that this is going to improve Arctic coastal monitoring. This is really seen as an important thing. There's lots of research and government documents that are stressing this, not only because the processes aren't fully understood and that there's communities up there that are vulnerable to this change, but it's also it's an indicator of climate change. And then finally, we ultimately want to try to get a better estimate of the contribution of carbon dioxide and methane being released from our coastal erosion, this organic carbon decomposing from Arctic coasts, and what this consequence is for global greenhouse gas levels. And I will just finish by acknowledging funding partners and my summer field crew, and pass it over to Patty for questions. Sure.
Go ahead.
Thanks for the talk, Andrew. I was curious if I'm misusing the terms, forgive me, you correct me. I think when you were talking about the step of segmentation,
Yeah.
I believe you said there's a lot of trial and error. I'm curious as to how do you know when you're there?
Right. Maybe I misspoke, but the trial and error is in the refinements. So the segmentation is kind of just like a first step in classification. The refinements would come, which is kind of, the segmentation is sort of independent of the human. The refinement comes in when it's up to the human's expertise to say, to apply different rules, if that makes sense.
So how do you, I'm just curious as to how do you know when you're satisfied that this is where I'm at? Is it you have very specific ground truth in one spot and you say, okay, that's nailed that, so I'm satisfied now? Or?
Yeah, I think there would be a combination of ground truthing for sure, and just sort of going through as an iterative process, trying to, I think it's, yeah, based on human knowledge of the ground that will ultimately validate what the best rule set is going to be.
Thanks. Anybody else?
Fine by me.
Okay, move on. So, Patrick Duke, also from Geography. Let's find you.
I'm risking it. It was jumping all over the place. That's okay.
Okay.
Thank you. So my name is Patrick. I'm a master's student in geography. My supervisor is Brent Ellis. I'm in the same lab as Sam Jones, who's up next. And today I'm going to just talk quickly about evaluating autonomous marine carbon system sensors in Cambridge Bay, Nunavut. Whoa, the risk. Yeah. So I'm just going to start with a familiar figure. So this is the Kneeling curve from Mauna Loa Observatory. This is the atmospheric concentration of CO2 over time, and as you can see, it's increasing, and this is driven by anthropogenic emissions, which are driving climate change. And when you look at this, the impact can't just be in the atmosphere, and it obviously isn't. The ocean is another major kind of reservoir of carbon that is uptaking or sequestering anthropogenic emissions every year, and that's kind of leading to a lot of different changes in that environment. So we're seeing ocean warming, we're seeing oceans become more acidic, specifically at the surface, and we're seeing kind of oxygen-limited environments in the ocean. But the kind of biggest question is what's happening in the Arctic. So we have a lot of information. We have a lot of information about what's happening in kind of the global oceans, but there's a lot of observations missing in the Arctic. We don't have the monitoring necessary in the Arctic to actually see kind of what is happening and help modelers, just like Andrew's project, kind of observational scientists contributing to facilitating models, getting kind of narrowing the uncertainty. That's exactly what we're trying to do. So we're trying to provide a method for using innovative autonomous sensors in the Arctic to improve these observations, to actually give models feedback to kind of narrow that uncertainty and really kind of narrow down what's happening in the Arctic with response to climate change in a warming world, and also help kind of policymakers with, are these decisions being made now adapting and mitigating to climate change kind of the way that we want to go. So that's kind of the direction of this. And these are two words that were provided to me by one of my friends in Cambridge Bay, kind of like learn and ocean, and I really like attached to that, and I was like, that's pretty cool, and that's something that I'm trying to contribute to. So this is kind of how previous carbon system studies happened in the ocean, in the Arctic Ocean. It was all opportunistic icebreaker surveys. So these are surveys that are taking place on board the Amundsen, for example. This is one of my lab mates' photos, and it's kind of these opportunistic surveys where it's skewing observation, it's biasing observations. It's skewing them all to kind of like ice-free conditions, summer months, and very like temporally limited data sets. So there's a lot of studies out there that are like this, and that's great. They've contributed to a lot of observations for us, but kind of this temporally limited data set, it's all happening in the summer. How can we expand that a little bit? So that kind of takes me to what I'm trying to do. It wasn't worth the risk. Oh, we're moving. So this is the question that I was trying to answer. Can we utilize innovative sensor technology to increase temporal coverage in the Arctic when we're observing the marine Arctic carbon system? So these are just some... So these are just some headlines I pulled out just to like really drive this home about how important this is. Us as taxpayers should look at these values and think like, this is something that's actually happening. So don't read all the text, but just pay attention to the big ones. So 5.6 million, the government is investing. All these are headlines from the last like 3 weeks. Ottawa has committed to invest in a global ocean observation platform that utilizes innovative autonomous sensors. And then one of the key focuses of that is Arctic ocean ecosystems. So that's kind of the background of where we're coming from, and lots of groups are working on this. There's a group at Dalhousie that's coming out with some pretty cool international collaboration stuff with marine robotics and developing autonomous marine systems. And the new Canadian Integrated Ocean Observing System is a big one that's going to take a lot of money from taxpayers, obviously. But one of the key highlighted pieces there is Arctic issues. So it's dealing with a whole bunch of things, but all these innovative autonomous sensors are trying to address this kind of like Arctic piece differently. And I'm kind of offering that context here. So Ocean Networks Canada, they've done a lot of great work on this and kind of have led the way. And the Cambridge Bay Observatory is a real key piece of that. So it's just in Cambridge Bay on the southern shore of Victoria Island in the Northwest Passage. And it started in 2012, but then we just kind of like got the carbon system sensors on board in 2015. So the platform, it's kind of just off the dock in Cambridge Bay. These are some of the guys from Ocean Networks Canada that are working on board and trying to deploy that, the platform just last year. So it's just off the dock. It's in about 7 to 8 meters of water. So it's not very deep, and it's very near shore. It's cabled, so then all the data is actually live streamed over the Ocean Networks Canada site. So you can see any of this data. It's also encouraged that the community take a look at this stuff. They have sort of a near shore station as well for atmospheric measurements that are pretty helpful for providing insight into just kind of what's happening, as well as cameras, so you can actually see ice coverage at certain times of the year. What does that look like throughout the deployment? Dude, you're just flicking through, man, and I'm just like not moving.
There, it always
Oh.
changes. Maybe you're too close to it or something.
Yeah, I don't know what's up. So
Too far.
too far from the thing? Okay, I have a hard time standing still, obviously. So this is what makes the site unique, in that it has first-year sea ice and the temperature and salinity changes. So in the top, you can see this is ice thickness over time through all 3 deployment intervals that we're going to look at. And you can see kind of ice formation in mid-October, breakup in late June, and then reaching a maximum thickness of just over 1.5 meters. And then you can see that the temperature salinity changes, salinities in blue, temperatures in red, through those 3 deployments also vary quite a bit. So it's an estuary ecosystem, there's large changes. So this is a great testing ground for these sensors if you're looking at broad-scale Arctic deployment, in that we have temperature changes of upwards of 10 degrees, as well as sort of 5 PSU changes in salinity through that deployment interval with the same sensor. So once the sensor is calibrated and then put in the water, you're actually not recalibrating until you pull it out. So that whole year-long deployment, the sensor's operating autonomously. So that brings us to the sensors that I'm actually working on. So it's the CFET pH sensor and the ProOceanus CO2 sensor. Oh. So this is the ProOceanus. So this sensor is measuring PCO2, or the partial pressure of CO2. The way this sensor works is it kind of gas equilibrates across a membrane in the sensor with the seawater, and then it moves into a detection cell. And then from there, we measure CO2 concentration and the total pressure, and can use that to project the partial pressure of CO2. The way this sensor kind of was operated for this long-term deployment is that it has an automatic zeroing calibration. So every 12 hours, it'll actually close that loop and then run through a CO2 scrubber where it's going to strip CO2 using soda lime, and then we can get this zero measurement. So every 12 hours, we have an automatic calibration throughout the deployment to kind of give us this zero value, which really helps for these year-long deployments where you can't operate the sensor or can't calibrate the sensor with onboard standard gases, such as in the Arctic. And then the CFET as well. So this is measuring pH, a measure of acidity, and it's built for these long-term deployments in that it has 2 independent operating electrodes. So it's measuring the pH value independently with 2 electrodes. One is internal, so it has a silver chloride housing, so it's not interacting with the seawater. So any changes in salinity, that electrode actually won't incorporate into that pH measurement. The external electrode, however, is interacting directly with the measuring medium, so directly with the seawater, and the salinity changes will affect the pH that external electrode is measuring. So in order to properly calibrate these sensors and evaluate them, we had to collect discrete samples to give us PCO2 and pH values that we could actually compare to the sensor measurements in situ. So we started, thanks to NSTP, in January of last year, and then this continued through the spring, kind of during ice breakup, as well as into the summer, into the open water season, and then even into the fall when we're actually starting to get ice breakup, and the system can be very dynamic. And this is kind of what that full time series looks like. You can see this is PCO2 measured by the ProOceanus through those 3 deployment intervals. And then we have the little black dots are our calibration points. So that's what we measured with discrete sampling of PCO2 at all those time intervals. So you can see the first year looks pretty good. The second year doesn't look great compared to those discrete samples. And the third year, it does look pretty good trend-wise, but there seems to be quite a bit of displacement. So this is something that we can correct for. And when you look at the kind of those matched up sampling points from the sensor and from the discrete samples, you can see kind of a few different things. So on your left is the 2015 deployment. Right in the center of the screen is the 2016 deployment, and on the far right is the 2017 deployment. So just kind of focusing on the root mean square error values there, that's kind of our estimate of how these sensors are performing. So root mean square error for the first deployment is about 5.6. That means our sensor accuracy was about 5.6 ppm, which is quite good. Like, this is within range of kind of what the ocean observing platform recommends for carbonate system measurements. The second year, where things didn't look so hot on that last graph, you can see that the root mean square error, 45 ppm for PCO2. This isn't a very good measurement. And then in the 2017, you can see 2.9, but this C0 value is the sensor offset. C1 is the sensor drift. It seems to line up pretty well with where we're getting that root mean square error, or the sensor accuracy. So I think this is something we can adjust for the sensor offset. And we'll kind of touch on that and why that is a little bit later. So here was the pH sensor. So actually, the first year the pH sensor was in the water, it failed 3 weeks into deployment. So we actually only have the 2016, 2017, and then 2017, 2018 data set, which is kind of unfortunate, but I think that's the way this works. Put expensive stuff in the water, break it, and then kind of make some changes. That's the way these always seem to go. So here you can see in the blue is the external electrode that's measuring pH, and then in the black is the internal pH measurement. So again, the external is sensitive to changes in salinity, the internal isn't. And you can see these red dots are kind of where our discrete samples lie based on the sensor data. And the first year, that 2016, 2017 deployment, it doesn't look too great. There's a large difference, especially between the internal and external electrode throughout the deployment, especially in the starting kind of first 2 months. And then in 2017, 2018, it actually looks quite good, especially with the external electrode that accounts for those salinity changes. So that brings us to kind of plotting those two, what the sensor's measuring and then what the discrete samples are measuring. And the root mean square error here is not bad. It's just outside of kind of what's recommended for pH carbonate system measurements globally, which is about 0.02 pH units. So here, the first year, the internal electrode is about 0.03. It's not great. And then the next year, 0.029. So that's not too bad. So 2017, 2018 deployment looked quite good, actually. So just looking at why these deployments maybe don't go so well, it's preconditioning. So before you put these sensors in the water, you really need to think about where they're going and how long they're going to be in the water for. So this is kind of illustrating that preconditioning. So here in blue, we have salinity, and then in black, we have the difference between the internal and external pH values. So you can see kind of the very dynamic environment, especially in like September of 2016 on the far left of the graph here, of how salinity is changing quite a bit through September, and so is that difference in pH values measured by the internal and external electrode. The pH difference is greater than kind of 0.1. Ideally, this would all be along that top frame rated 0. There should be no difference. But you can see that there obviously is a difference, and that dynamic environment played quite a role with that external electrode accounting for salinity, with the internal electrode not accounting for it. And the best way to do this, kind of to prevent this, is to kind of precondition all these sensors before they go into the water with in situ conditions. So the next year, kind of looking at what happened previously, the group that I'm working with decided, hey, let's actually precondition the sensor to salinity and temperature values that this sensor is actually going to be measuring right when it puts in the water. And you can see salinity isn't quite as dynamic that next year in September of 2017, but you can see that the difference between the internal and external electrode are very much the same throughout the year, which is great. And that shows that these deployments are fairly stable. And that kind of brings us to correcting the data. So based on salinity, temperature, and then what the discrete samples are telling us, I can actually look at the sensor voltages and make corrections. So correcting as best I could, I managed to get that 2016, 2017 pH measurement to a root mean square error or sensor accuracy of 0.03, which is not too bad. And then 2017, there wasn't a ton I could do with this one. I tried a few nifty kind of shifty things with multi-point calibrations and single-point calibrations and end of deployment, start of deployment, and this one didn't change a whole lot, but that's great because it's showing it's fairly stable. And then the last kind of piece here is co-deploying biogeochemical sensors on these platforms. So great, we have PCO2 readings, we have pH readings, and the accuracies are very much what I'm concerned about. The best way to look at that is have something else on board these platforms that is also measuring biogeochemical kind of indicators. So here we have pro-oceanus PCO2 data in pink, and then the oxygen data from a seabird Rinco sensor and in blue. And you can see these kind of like mirroring each other very much. So that's great. You can see that through the fall and into the winter, PCO2 is increasing every year, and oxygen concentration is decreasing every year as respiration sort of dominates the system. And then you can see right around late winter, early spring, right when the sun kind of comes up and there's enough to kind of penetrate through the sea ice, you can see that sort of flips. So PCO2 concentration is decreasing, and then oxygen concentration is increasing as we have photosynthesis dominating. And this is great. Like, we can see that these two cycles mirror each other very much, and that what we're getting with the PCO2 sensor is actually something fairly accurate. And the R-squared value is not too bad. So that's kind of all three pieces of kind of recommendations going forward with kind of those sensor development that's taking place, as well as sensor deployment, specifically in Canada, with a whole bunch of your money and my money. So 5.3 million and 3.8 million. There's a lot of funding going into these projects, and I think it's important to evaluate the sensors particularly well before and kind of see the feasibility of these projects. So kind of recommendations based on our study of how these deployments should look. The frequent collection of discrete samples throughout the deployment. This is something you can use to check your sensors and kind of see how are these deployments successful, what's the accuracy going kind of throughout these long-term uncalibrated phases. And then appropriate pre-deployment conditioning periods, putting these sensors in situ conditions and kind of letting them, calibrating them and working with them beforehand before actually going into the water, especially if the environment is fairly dynamic or very different, like negative 1.5 degrees for our deployment for most of the year is not something these sensors were built for. So it's something to consider. And then co-located marine biogeochemical sensors. So having an oxygen sensor on board is awesome for having that PCO2 sensor. And then you can kind of say, okay, are they mirroring each other? How do the cycles look? Is this very biogeochemically tied? And this just gives you more insight into the sensor performance. So I think that's it for me. Thanks, NSTP, for paying for a lot of my stuff.
Good. Thank you. Any questions? Yes.
So you showed that platform with a bunch of instruments on it,
Mm-hmm.
and the instruments looked really close together. And I know in the Wi-Fi code, like everything behind the scenes is lined up,
Like
like
a certain way.
yeah. So I guess my question is, how do you avoid sensor interference with one another? Do you use a strategy for that, or are they assumed to just work okay in close proximity to one another?
So it was one of these pictures has a pretty good image.
Yeah,
So this one here is pretty good. Yeah. So I can actually the intake for the PCO2 sensor is actually right here, and then the intake for the pH sensor is actually back here. So this long tube is the pH sensor, and then here's our pro-oceanus. And kind of as you're assuming that it's always measuring the same thing, right? Like that's the biggest thing. And for such a long deployment interval, I think these assumptions are fair. If you're looking at like diurnal cycles particularly, then you may see a difference, particularly how close this is to the seafloor. If there's something different in one little patch and something different in this next little patch, you could definitely be measuring something different. But I think like over the course of a 365-day deployment, I think we're okay. And this is something that a lot of these guys have thought about that put this platform together of like specifically where the intake is for seawater to each one of these sensors. And I think the spacing is quite good. Like hopefully you don't have intakes right beside you, like something where it's actually releasing seawater, going through one sensor and then coming into another, that's something that, you obviously don't want. Yeah?
I have 2 questions for you. First of all, it was interesting to see the comparison of the different data sets to see what the accuracy was. But it looked to me like there were some gaps in your data.
Right.
What causes those, and can that affect the calibration?
Definitely. So actually, in total, so the gaps in the data are from power outages. Cambridge Bay, power, it's not just to the platform, it's to the whole town. So this is something beyond my control. And it's just something you gotta deal with. Like there's particularly outages where, you go and collect a discrete sample and it turns out the sensor was down for, 4+ hours. How useful is that sample? I ended up throwing all of those out. So in total, we had 39 discrete samples over the course of 3 years, and I think like my total end data set was actually around like 22, which is disappointing, but it's something that you can't do. And also like those discrete samples do end up contributing to when you go and actually look at the science behind the data. Great, the sensor worked, now let's evaluate what's actually influencing the system. So it's all gonna be put to use for sure, but it is definitely disappointing.
So that's a perfect segue into my next question. How does this isn't in terribly deep water, is it?
No, this is
You might have some wave action.
like 7 or 8 meters, and it's very close to shore.
So how does, if you're leaving it there for a whole year or multiple years, sediment raining down on it impact her big?
Right, so it's 1 full year. It gets pulled out of the water, everything gets taken off, put new sensors on, recalibrate, and then put back in the water. So they're clean, full clean. But definitely at the end of the year, biofouling is like a big question with a lot of these sensors, particularly with pH. That's why having that external and internal electrode are really important. The external electrode is definitely going to biofoul. Like it's just how much. So kind of near the end of the year, seeing that those differences in pH between the external and internal are actually quite good means that I think biofouling is maybe just in this estuary isn't something we have to worry about too much because it's not super productive at this level. We do see some like subsurface chlorophyll maximums and phytoplankton blooms, like 30 meters depth, but at 8 meters depth, it's looking okay. Like it's not super sandy or silty, and yeah.
Great. Thank you very much.
Maybe this side. Is that okay? Sound-wise? Yeah? Oh, yeah, it's that thing.
Do you want to see what you can do about that?
Oh. Let's see, is it still? Oh, no, it's okay. I don't know. All right.
All right. Our next speaker is Samantha Jones. Looking forward to hearing.
All right, thank you. Yes, geography again. We're taking over your whole night. So today I'm going to talk to you about carbon cycling, and I'm going to use a case study from Freshwater Creek, which is one of my study sites, and it's also in Cambridge Bay in Nunavut. And I'm particularly interested in the inorganic carbon cycling, so related to what Patrick just talked about, carbon dioxide, and also the products that form when carbon dioxide is dissolved in water. And I'd like to start with some of what we know about carbon dioxide and inland waters, or rivers and lakes. We know that they're important players in the carbon cycle on a global scale, and typically they emit CO2 to the atmosphere. Particularly hotspots are some of the smaller streams, so lower order streams, headwater streams, and we see lots of emissions happening there. And under ice in the winter, we see accumulation of CO2. So when you have seasonal ice present, you tend to get a buildup of gas that then is released when that ice breaks up in the spring. And we also know from studies in the literature that rivers are not just conduits for CO2. They also are active sites of transformation and processes that convert carbon from one form to another. There's a lot of things that we don't know, and this comes to bring me to some of my objectives and some of the things that inspire me to do my work. So compared to lower latitudes, we have relatively fewer measurements, and Patrick touched on this a little bit, that we see some studies, but especially in the Arctic, we have this seasonal knowledge gap as well. And when it comes to time series data, we don't have long-term coverage where we're repeating measurements at regular intervals and looking at big picture, long-term scales and seasonal variation. There's also some question about whether or not we can take what we know about these systems from the lower latitudes and apply those in polar environments. There's some uncertainty as to whether there's unique characteristics in Arctic rivers and streams that might make biogeochemical cycles a bit different. So we want to investigate that. And then there's a lot to learn about interactions and feedbacks. So typically, different environments like inland waters and the ocean are studied in isolation from one another. They are researched by different communities of scientists, and even in inland waters, often lakes and rivers are studied by different groups of people. And in my project, I'm interested in looking at a lake, a river, and the coastal ocean, and integrating communications and linkages and feedbacks across systems. But today I'm going to focus mostly on the river part of things. For my thesis, my overarching objective is to quantify CO2 fluxes. So looking at the movement of carbon dioxide between different environments, so the lake, the river, and the coastal ocean, all in one continuum. And then looking at the linkages and the feedbacks. How do they communicate with one another and impact one another? And then what are the vulnerabilities to future change? Now, when I talk about fluxes related to the river, that really is going to culminate in two numbers when I have my thesis outcomes. There'll be a number that is the annual emission from the river to the atmosphere, and then there'll be a number that is the annual discharge of dissolved carbon dioxide from the river out into the ocean. But today I want to show you that there's a lot of things happening behind the scenes of those two numbers. And I'm going to show you some seasonal variations. I'm going to show some short time cycles, and then convince you that it's really important to understand and appreciate those things in order to make your flux estimates. And I'm also going to show you how you could use that to plan your data collection. The impact of my project will be fourfold. So first off, I'm looking to help establish baseline in my study area. So it's hard to predict vulnerability to future change if you don't understand what's happening in the present. So I'd like to look at Cambridge Bay, look at the river system, and be able to characterize what's happening now. Then this can act as a framework for other processes. It could perhaps act as a constraint in some larger picture models or studies where they need more hard data points in these polar environments, and then potentially be an analog for other regions where you can't access the site because of logistics, expense. It's a challenging place to get to, so you can't, of course, study every river in the Arctic. This is what my study area looks like. So I work in Cambridge Bay, Nunavut, similar to what Patrick just showed, and I've got a star on the Canada map up there to get you honed in. And then I work across three environments. So Cambridge Bay, which is the coastal ocean, estuarine environment, Freshwater Creek, which will be the focus of my talk today, and then Granier Lake and the watershed, which is outlined in red. And I go out and I collect time series data collection, of course, with the help of a large team, because this requires someone being out on the ground pretty much weekly, all year round. It slows down in the winter when we do monthly to seasonal sampling. But we go out, repeat our sampling every week, collect sensor data, so look at things like temperature, conductivity, dissolved gases, dissolved oxygen, pH. We also collect water samples, and we bring them back here and analyze some parameters in-house, and we also have some that are sent out to collaborators or commercial labs. So we do the dissolved inorganic carbon and the alkalinity, which are two of the carbonate system parameters that we need to characterize the carbon cycle. And from these, I'll be able to calculate the PCO2, which Patrick just talked about. We also do stable carbon isotopes, which give us some information about the sources of the carbon dioxide and the processes that are impacting it. We look at stable water isotopes, again looking at sources of water, and then dissolved nutrients and methane. And out of all of this information, we'll be able to calculate fluxes with also input from weather station data and gauging station information as well. This is a map of our field area, and this includes more than what I'm going to talk about today. The blue dots and the orange dots are the data I'm going to show you in the rest of the presentation, but I've also got the other transects that we do as part of our group. So some of the stuff that Patrick just talked about is from the red transect, the main line. So we've got lots of supporting information in the coastal ocean as well. And the frequency of sampling at these stations depends on the priority of the station. But we collect our sensor data at all of these sites, and then we have selected sites on each transect where we collect water samples. And this is an example of what the time series looks like. So this is in 2017, and we repeated this again this year. But you have a graph that shows the date on the bottom and then the river discharge on the y-axis. And so Freshwater Creek is gauged by Environment Canada. And this has some humps and bumps because it's the real-time data. They'll release a QC'd version of this. And then the black triangles show our sample dates. So you can see we've covered all of the different parts of that hydrograph. And then in 2018, we have even more sample resolution. So we'll see an improvement on our coverage. And now I'm going to show you some of the cool things that I've been finding. The first is that at the very beginning of breakup, when we start to take the measurements in the river, we see elevated amounts of the dissolved inorganic carbon. So we've got this interesting buildup of carbon dioxide dissolved in the river. And that's reflected in both the DIC, the dissolved inorganic carbon, and the total alkalinity. And then after this peak passes by, it calms down to a more moderate level, which is controlled by the local geology. And we also see that this influences what's happening in the coastal ocean. So the river site's up in the right there, Freshwater Creek, and I want to draw your attention to B1, which is a sample site in the middle of the bay. And when we look at the influence of this pulse of elevated carbon in the water, it's reflected in the coastal ocean. So you can see on the bottom another version of the plot that I just showed on the previous slide, and then a peak in the surface water of B1 that reflects that input of dissolved inorganic carbon coming from the river, which is ultimately coming from the watershed. And you can see that this peak passes pretty quickly in the surface ocean. So there's some questions about where does this go, how is it processed, but we also want to know where does it come from, because the river freezes completely to the bottom at the end of fall. So we know that the gases can build up under ice over the winter and the spring, but it's not happening here because there's no water under the ice. The little hole on the right photo is just about an inch or two, and then it's the gravel on the bottom. So we've got to look upstream to look for where this accumulation is happening. And so in 2017, I was really focused on the river. When I went back this year in 2018, we repeated the river, but we also went and surveyed the lake. And we found some cool stuff. This is a transect in the lake that goes from on the right towards the mouth of the lake, where it connects up to the river, towards the middle of the lake. And the colors are showing dissolved oxygen percent. And you can see that there's some zones of very low oxygen in the lake. And in the deep water, in the middle of the lake, it's low oxygen, and also in the shallower station towards the mouth, it's very low oxygen. And in this area, towards the mouth of the lake, it's got very irregular bathymetry, and we also have zones where the ice is frozen completely to the bottom. And so I think it's compartmentalized, and then those segments that get separated from the rest of the lake or don't have very good circulation are becoming anoxic, and then you're having the gas generation in those zones. And then it has nowhere to ventilate to because there's ice on the top of the lake. And if we look at the GL water station, that stands for Grainier Lake Water, that's our sampling station, and we have a time series data collection there. And this is what that looks like. So in the center of the lake, in the summer, which is the orange and the purple line, we have a very well mixed water column. lots of oxygen in there. It's actually super saturated in oxygen, more than 100%. And then as we get ice on top and we move into the months where it's disconnected from the atmosphere, that oxygen gets depleted over time and even approaches anoxic conditions. So once you get under 30%-ish oxygen, you enter kind of a hypoxic region, which is not suitable for a lot of aquatic life. And so this is interesting because those are the zones where I think that gas generation is happening. I also look at isotopes of the water molecule itself. And my motivation here is to understand a little bit about the sources of water that are in the river at any given time, and to look at the timing of when those sources are present and when they go away. Because each different source of water is going to carry with it a different carbon pool or different characteristic. And so if you're not familiar with isotopes, there are different versions of the same element that have different weights. And because they have different weights, they get sorted by different processes, whether it be physical or biological. And so when you look at the different measurements or the ratios of isotopes in the water molecule compared to standards, you can start to make some inferences about sources and processes and what types of water you have. And what I want to show here is that we have kind of these very light or depleted isotopic compositions in the snow, which is shown on the bottom left, and then the lake values are heavier, and the river changes composition from the beginning of melt as you move towards the open water season. So it starts more like snow and then becomes more like what is in the lake under the ice as that lake breaks up and connects up and becomes drained by the river. And so this is important because we can look at the inorganic carbon behavior of the river, and we can start to break it up into different phases where you have different behaviors and different carbon loads. So the first thing that happens is you have a few days where the river starts to break up, but nothing is connected up yet. And so you've got lots of water coming in, but it's mostly just snow melt and it's on the surface. And so that is very depleted in inorganic carbon. Then you break up things enough that you link up the lake. And that's when you release this pulse of the carbon from the lake into the river, and it's being delivered out into the ocean. Then the pulse passes by and you sort of enter this moderate, regular flow that's influenced by the geology, and that persists until the river freezes up. And then you enter this kind of fourth phase where it's completely frozen, so there's no contribution either to the atmosphere or to the ocean. And then you could argue that that moderate DIC phase, you might want to break up based on the amount of water that's coming out of the river. Maybe the peak flow is different than the falling limb. We also see daily cycles. So Patrick was lucky enough to share this experience with me when we went out every 4 hours and sampled the river. And we also had another day that was done like this earlier in the summer that a research assistant and a local field technician completed. And we looked at what's happening over a single day and can we see anything interesting. And this was really inspired by a paper that came out of Scotland by Waldron and others. And they found that when they looked in the river and measured oxygen and CO2, including isotopes, over a day, they saw this back and forth kind of picture that Patrick showed, big scale with the sensors in the ocean, indicating that sometimes you had more oxygen, sometimes you had more CO2, and this was a result of more photosynthesis in the day and then more respiration at night. And so that river was actually actively transforming and reworking the carbon back and forth. And so I wanted to see if we could see something like that in our river. And sure enough, we saw something. Over the day, we've got oxygen, which is on the left here. The ODO just stands for optical, which is the type of sensor we use, and then pH on the other side. And the reason I have pH is because it reflects acidity. So lower pH is more acidic, and the water is more acidic because when CO2 dissolves in the water, it becomes more acidic. So here I'm showing you that during the day, we have higher oxygen and higher pH, which means less CO2, and then overnight, we get more CO2 and the oxygen subsides. And so the point of all this is that depending on when you sample, you're going to get a different answer. So you need to think about what season are you sampling in, where are you on that hydrograph, and what time of day are you sampling even, and are you consistently sampling at the same time? Because if you're going to estimate flux, you need to understand where your estimate is coming from and if you're biasing your data based on the time of year or the time of day that you're collecting your information. So just to wrap up, these are my key results to date, but I still have a lot to do. So right now I know we have elevated DIC during breakup. Breakup is a special time in these environments that have seasonal ice in terms of gas exchange. The creek influences the coastal ocean, and this pulse is coming from the watershed. We see that there's at least 4 different behaviors or phases in the river, and that depending on where you collect your data, that's going to influence what you calculate. And the other thing to think about is if I'm looking at literature data, to really be mindful of when did they collect it, do they report time, do they tell me anything about the metadata that might help me interpret the information. And then what's next for me, hoping to do at least one more field season. I want to continue the time series data, working on water sample analysis in our lab, and that will also include the carbon isotopes, which is going to help additionally with timing and also source. Working on data interpretation, refining that conceptual model based on what comes out of the water sample analyses, and then calculating the fluxes. And then I return to my big picture project and look at how to integrate this with other environments, so the oceanography piece, which I didn't talk about at all today, but is also going to be a big part of my dissertation. That's it, so thank you. Yes.
So I'm so glad you showed that you're going to go back in the field.
Oh, good.
Because your third last letter, whatever it was, sparked a question.
Yes.
And that was, you know that the CO2 changes through the year,
Mm-hmm.
and then you discover that it changes through the day. Does it change by the minute or the hour? Does it change by the minute or the hour?
I don't know about, I feel like there are other changes, and it could change by the hour. I guess it also depends what's going on in the lake. And I think the change that we will see in the different time periods will be different. So we also have, with the other 24-hour day that we have is from when there was snow. And I didn't show that here, but that shows a different thing altogether. The signal of the snow melting in the day and then like easing off in the night completely overwhelms the other signals, it looks like at a first glance. So I think in terms of DIC change, there might be different time gaps depending on what's happening. So it might be different when there's still snow on versus later on. The other thing that's happening on that falling limb is evaporation, which I haven't investigated yet, but that could potentially change things in the daytime as well. But I mean, we could go out and do some continuous monitoring. We do have equipment for that in our lab, and hopefully we'll be getting maybe some more things that we can compare. And that's probably the biggest piece that is not included in my work. We could take one of these boxes and sit it beside the river and do our regular stuff, but also have that continuous, and that would maybe help address that question.
Awesome, 'cause then you can see how much.
Yeah, how much noise you have. But
you can just see during the day, as the sun's moving around,
Mhm.
things are kicking in as you described. But there could be all kinds of things, right? Little streams.
yeah.
This point, that's no batch melting, and that's no batch melting.
Yeah, absolutely. And the other thing too that, and it was a hunch, but it worked out, was the first year we were just sampling every week. And then I sort of felt like maybe we should just sample at the same time every day, because let's just take out variables that we don't need. And then once we did this, so what we ended up doing, because it's not practical for it to be exactly the same time, is I talked with our local field assistants and asked them, would it be better to do this always in the morning or always in the afternoon? And so they do it kind of within a 3 to 4 hour window, but it's always afternoon. And so we were just, for the regular sampling, we've done it this year, always kind of the same time. But we could also try some other things like sampling twice a day, or to get a feel for for some variation. Yeah.
Non-technical question, and everyone else knows the answer, forgive my ignorance, but I see Polar Knowledge Canada there. Are these studies being done around Cambay being done there because of the research station?
In part, yes, I'll have to be honest. Yeah, so I mean, Cambridge Bay is super cool because I've got this neat continuum, everything's within a day trip. Like, I'd like to say that's the only motivator, but the logistical support from having the research station there allows us to do a ton of things that we wouldn't be able to do otherwise, yeah.
Not to add more work for what you're doing up there, but I'm curious, you talked about having a lot of the analyses done in the lab here. Is there not the ability to do that in the research station?
Right now there isn't. In the future, it's possible. A lot of our equipment is portable. They say it's portable, it's still really large. But in theory, it's portable and we could move it. The research station will be opening an entire second building that has lab space. So in the future, we might be able to move some of our stuff there, or even potentially use some of their equipment if they duplicate some of the equipment we have here. But right now, for the water sampling, we've got to bring everything back with us. And the same goes for like things like bringing stuff we need. We've got to bring everything in, and we have to take everything when we leave as well. Yeah, so we pretty much start fresh like every time we go up. Yeah, thank you.
And just one follow-up that was mentioned earlier. Does the research station have its own independent generator? So if the
Oh.
sound goes down, it's still...
Well,
Are you suggesting Patrick plug into the wall?
I'll tell you, I would probably guess that they do. I know they have an emergency generator, but I do know that the apartments do not, because when I was there, speaking, I laughed when he said that, someone hit a telephone pole in the town and it knocked out the whole power to the town, and we didn't have it at part of the research station, but I'm assuming in their area that would be sensitive with experiments and stuff, they would have it there, because they have freezers and all kinds of stuff that needs to stay online. Yeah. Yeah, thanks.
Thank you very much. Closer to the middle, the better. You can turn your head more freely.
I tend to move around a lot. It's always good to have an anthropologist at the end and not the beginning. So anyway, my name is Kent Spiers. I'm a PhD candidate in the Department of Anthropology and Archaeology. I'm in my fourth year, and I had hair, so you can tell how well it's going. So anyway, I'm a social scientist. My background is in sociology. Both my undergrad and master's degree are in sociology. And I thought to make things more complicated, I would become an anthropologist before this is all over. So keeping that in mind, social scientists, we like to be social. We like to talk to people. Sometimes we like to talk to groups of people or individuals. And so it was very important for me to find a project that involved talking with a lot of people. So that's how I came to this project, which I'm calling Lessons from Pond Inlet, How to Create an Inclusive Community-Based Monitoring Project. So I'm going to take you back a little bit after we talk about this for a second about sort of how I got to this project and the research question that I developed out of it. But a lot of people say, what is community-based monitoring? There's a lot of different definitions out there, but the definition that I first read and sort of have stuck with is this one, which is a process where concerned citizens, government agencies, industry, academia, community groups, and local institutions collaborate to monitor, track, and respond to issues of common community concern. And that is open to quite a few different areas. We talk about water quality, we talk about housing, we talk about coastal erosion, food security, et cetera. Those are sorts of the things that came to mind when I was looking at that. So back in 2014, in my early days, I was stumbled upon this atlas of community-based monitoring, which is over here. And having read this definition of community-based monitoring, I thought, oh, this is great, having projects where people come together and you sit down and you have an issue and you think about how can we figure this out. You bring scientists together and you have them talk about what you want to understand, how you want to figure out the problem, how you're going to measure it, and how you're going to analyze it, and then what are you going to do about it. So I thought, great, there's an atlas which has got to be featuring hundreds of different projects that show just that. Needless to say, back in 2014, there wasn't a lot. There were a total of 79 projects that were on that website. None of that information was downloadable. I had to click on every single one of those yellow dots, so that was a lot of fun. And my supervisor, Mary Beth Murray, and I were talking about, how do you create a community-based monitoring project that community members are able to be a part of it, are able to help with the collection of data, help with the analysis of data, and then that big question of afterwards, what do you do with that information? How is that information accessible? So we did a little bit of an analysis where we looked at each one of the 79 projects that were on the atlas, and 64 of them at the time were in progress, 11 of them were complete, and 4 of them were on hold. Various reasons, such as budgetary concerns, was one of them that I can remember. So then I asked the question, how many of them had a website? So out of those 64 in progress, 49 of them had a website. Out of the completed ones, 7 of them had a website. There were some websites for the ones on hold, but they really didn't say anything. They just sort of said, come back later. Then we wanted to know, are there any data on those websites? So out of the ones that were in progress, 17 of them had data. Out of the ones that were complete, 2 had data. And then we asked the question of, accessible data, because it's one thing to have a spreadsheet on a website, which is great. You can download it and you can sort of manipulate it and understand what's going on. But we wanted to know, one, is it downloadable? Is it in a format that is conducive to being used? Or is it password protected? Or is there any sort of limitations to accessing that data? So out of the ones that were in progress, 13 of those projects had data, and 1 of the completed projects had data on them. So that made us sort of ask a lot of questions of, what's happening with these projects once they're completed? Or are we going to see the sort of same drop-off effect that we see with the ones that are completed with the ones that are in progress? And so we wanted to dig a little bit deeper into those projects and sort of monitor how that's going for those. But in the meantime, I wanted to find out a little bit more of how the community members are included in these various projects. So this isn't a great picture, but there's a lot more questions down here that the researchers, I think, scurry to just answer because there's very short responses. But a lot of the questions ask, is the community involved in the research? Most of them said no. Is indigenous or local knowledge a part of your research design? No. And so it just sort of made me question, if you're calling it community-based monitoring, why isn't the community involved? And why isn't local knowledge or indigenous knowledge being sort of put at the same level as the Western knowledge that's being used in these projects? So that sort of led me to formulating my research question. So what are the specific circumstances that prevent or facilitate a meaningful, productive, and respectful collaboration among scientists and northern peoples engaged in community-based monitoring programs? I won't read the rest of it for you. But sort of the idea is trying to find out what the community's experiences have been working with scientists. Did they feel that they were meaningfully involved? Were they part of the data collection? Were they part of the analysis? And sort of what was the the end of a project? Were they able to make any decisions based on what they found? So with that sort of in mind, I'd like to take you into my field work that I did starting in 2016 and then into 2018. So in 2016, I traveled to Pond Inlet, Nunavut on what I called a scoping trip, where I went around the community and talked to individuals about sort of my expertise. Tip, don't ever introduce yourself as an anthropologist because you'll just scare them. People don't want to talk to you. And talked to the Hunters and Trappers organization about sort of this idea of researching the researchers, we were calling it. I talked to the Hamlet Council as well. And there was a lot of support and a lot of interest in sort of understanding what the community's experiences have been working with scientists, and then finding out from scientists what sort of, why they're working with the community, why they're doing what they're doing, and sort of the other people that are choosing not to work with the community, just to sort of understand that. So a little bit about Pond Inlet. Population is 1,615 people as of 2017. It's a predominantly Inuit population, 94% are Inuit. The average age is 26.1, whereas the average population age here in Calgary is 37.6. The median income after taxes is $82,091. And I thought that was interesting because the median income in Calgary is $83,074. So a little bit less than a $1,000 difference. As you can see, it's located on the top of Baffin Island, right near sort of the eastern entrance of the Northwest Passage, or one of the entrances to the Northwest Passage. I guess that's debatable. And one of the other things that's important is that Pond Inlet's been this sort of hub for scientific research for 30 plus years. I've seen other people talk about it being 75 plus years. There's a lot of remains of scientific endeavors that have gone on for a long time. There's an abandoned building sort of over here called the Arctic Research Initiative. Two giant, well, pretty big buildings. They're just sort of abandoned now. Blue building there is Climate Change Environment Canada's research station as well. So I thought this is a great place to sort of carry out some research and to start answering my research question. So sort of what did I do and how did I do it? So this past March, I was in Pond Inlet for over 7 weeks. I hired 2 local research assistants. Up top there, her name is Ina Mukhtar. Down here is Michael Milton. They both were very instrumental in me getting the work done that I needed to. I interviewed a total of 28 residents. I thought 1.7% was a pretty big, and I was pretty proud of this fact, and I wish I could have deleted that after I saw your presentation, but just pretend that's good. Anyway, I did semi-structured interviews where I had to say, please talk to me for at least half an hour or an hour. And so fortunately I was able to interview 28 people. And as I said, like some of the interviews were about 20 minutes. Some of them went to about an hour and a half, but they were very rich, needless to say. So I asked people about their experiences with working on either community-based monitoring projects or simply just working with a scientist. That was sort of the prerequisite to being interviewed by me, is to have that. I did offer an incentive, and that's important for how my research has been changed since then. At first, I started off offering a $5 gift card to the Northern, which is one of the 2 grocery stores in town. When the first 7 people laughed at me about that incentive, I panicked and said to Ina, what can we do about that? I noticed that there was a bit of a gambling culture in Pond Inlet with local bingo on Friday night. Forget ever getting in touch with anybody between 6 and 8 o'clock because they're going to be playing their radio bingo. So what we did is, or what I did is I pooled the money together for the incentive into the chance to win one of 2 $100 gift cards, and then people were interested in doing the interview. The socialist in me wanting to give a part of it to everybody just didn't work out. I also did a presentation to the Hunters and Trappers Association, who has been such a great group to chat with and work with, very interested in the project. I also spoke with the Hamlet Council. The issue of incentives came up at the Hamlet Council meeting as well. One council member called me cheap. And I said, please forgive me, it's not my fault. I didn't come with a suitcase of cash, but it's led to other great things. And then lastly, I drank a lot of tea and got to chat with a lot of great individuals and got a lot of truly great information from that, which I'm going to be sharing some of that with you. So my interview questions, I had about 30 that I didn't always ask all 30 of them. It depended on the individual. But they range from interactions with scientific studies, the impact of scientific studies on the community, how have scientists engaged the community, because there's a lot of complaints about, people come to our town and they don't talk to us, or they're not communicating to us in the way that we want. So then I thought, well, let's ask the question of how do you want scientists to engage with you? And then the last question is, what projects would the community like to see taking place? So, I said to them, if you had me, a social scientist, standing in front of you and said, use me any way you want, what would you like to do? We got a whole bunch of answers as to the sort of projects that they would like to do. I also said physical scientists, but I said they're strange people. Just kidding. Yeah, because most of the scientific work that we're seeing it's coming from the south, or coming from the outside in, and it's really great stuff, but I thought, let's just ask the question of what they would like to see. So just some of the preliminary observations. I'm still analyzing the data. Part of the great thing about being a social scientist is that when you record people, you have to transcribe it, and when there's different dialects, it can take a little bit of time. So I'm still working on this, but the preliminary observation so far is the majority of the respondents enjoyed working on scientific projects. However, none of them were involved in the creation of the project or analyses of the data. Very few respondents were told about the results of projects. And this, to me, was a bit alarming because a lot of the projects had direct impacts on human health, such as contaminant levels in country food. One individual that I talked to was very excited about telling me about his project. He worked on seals, so he's a hunter. He goes out, he catches seals, he sends samples to southern Canada, and they're looking at contaminant levels. And I said, okay, great, how long has the project been going on? And he said, about 2 years. And I said, okay, what have you found? Well, we haven't gotten any data back. But to me, it seems like we got to really work on that lag time because a lot of seals have been eaten in 2 years. Few respondents feel that the projects are being carried out in their community to meet their needs. They think, yeah, okay, this is interesting, but I don't care about lemmings. That was one thing that they talked about, because there's a big community-based monitoring project dealing with lemmings. And there's a lot of other projects that they're sort of apathetic to. Communication of the community meetings is a major concern, as most residents don't hear about the meeting until it's already happened. Using social media was key for me. I don't know how about all of you, but I was trained that you're professional. You send emails from your university accounts. Dear sir, dear ma'am, I'm doing a survey. I'd like to talk to you. Blah blah blah. No one has ever responded to any of those emails I've sent. But I started using Facebook, and dear John, I see that you're here. I'd love to talk to you. I understand you're doing some water quality stuff. 2 days later, I see you read my message. You haven't responded. I walk around town a lot. I'll find you. No, but I found that the responses, people responded right away using social media. Phone, the people didn't want to phone you because it was just, they didn't want to pay long distance charges, et cetera. Plain language was very important. I have a picture I didn't include in this, but I'll definitely include in another presentation that showed a process map for the harbor that's being built in Pond Inlet. And I stood there for 10 minutes trying to understand it, and I couldn't understand it. I think that I have a bit of scientific literacy, but it's very complicated. And they said a lot of these presentations just are over their heads. This was really encouraging to see. The elders that I talked to were very excited to see that youth are involved in research, and they're encouraging that. And one of the last things that people talked about was that they encourage scientists to just be themselves. You know, when I asked the question, what would you tell a scientist when they are coming to your community? They said, just be yourself. Show us, tell us who you are. We want to know about who you are. So I thought that was important. Oh, and one of the other things when we talked about being yourself is they said, if you're coming to our community or coming to our house, you want to do an interview with us, don't knock on the door. And I said, what do you mean don't knock on the door? They said, just come in, because if you knock on the door, the only people that knock on doors in the community are the RCMP. And I said, okay, this is interesting, because I said, if you walked into my door in southern Alberta, I'm going to call the RCMP. So there's a bit of that education that goes on. And it took me a really long time to get over that we just walk right in and don't knock. So anyway, that being said. So what studies do people in Pond Inlet want to see? There's major concerns around the cost of groceries and airline tickets. I'm sure that I don't need to tell all of you that the cost of groceries is through the roof, but I was just sticker shocked when I was there. Overcrowded housing is an issue, and this is, you know, I don't think any of these are isolated to Pond Inlet, but overcrowding was an issue. And the fact that they said that we've talked about overcrowded housing for a long time, but we're not seeing anything done. No one's talking to us about it. They want to see more polar bear research, more seal research. They want to know, are they safe to eat? One thing that stuck out to me is one elder said to me, what is making us sick? Is it the country food? Is it the store-bought food? Is it the water? Is it the air? I don't know what's making us sick, but more and more people are getting sick. And we're flying more and more people out because Pond Inlet has a very small health unit, and a lot of people have to go to Iqaluit or Ottawa. Global warming was another major concern. How is this going to change our community? People talked about the fact that it's not as cold as it used to be, that storms are not as severe as they used to be, and that the wind is not as strong as it used to be. Narwhals and shipping. Baffinland is very close to Pond Inlet. There's a lot of shipping of iron ore going in and out of that region. So they want to know what the impact on narwhals is going to be with increased shipping. Talked about more Inuit knowledge studies and trying to educate more people about their cosmology or their way of knowing. And noise pollution was also a general concern for individuals. Okay, so the evolution of my research questions. So I'll try to make this very brief because I know we're done. So ethics kept coming up a lot. As any of you that have worked with people know that you have to go through ethics clearance. It's a really fun process and it's easy. So I want to make it more fun and easier. So anyway, what I kept noticing was I would hand somebody a consent form. They would sometimes read it, sometimes they wouldn't read it. If they did read it, they would say, why would I want to be anonymous? Only like 2 people said they wanted to be anonymous out of this. And I said, well, you know, ethics boards feel that if you say something that could get back, they don't want you to have repercussions of that. And they said, well, if I'm talking to you, I want credit for it. Okay, great. As I said, I got called cheap because my incentive was so low. And I said, well, you know, there's this whole voluntary nature. If I offered you a $50 gift card, they would feel that it's not truly voluntary. And they said, yeah, but have they ever lived up here? And I said, yeah, no. They said that, you know, university ethics boards really don't speak for us. I'm sure one individual said, I'm sure that your ethics board has never been to Pond Inlet. And I said, I'm sure they haven't. And so how can they speak for what our community needs and what our community wants? And I said, good point. Just do my interview, and we'll talk about it later. And then ethics guides need to be community specific. Regional ethics guides, national ethics guides don't really work. So quickly, what we're working on, and happy to report that it's going to happen next month, is we've got a group of individuals from Pond Inlet coming here to the University of Calgary to meet with the University Ethics Board, and they're going to sit through a very small portion of the ethics training that we get to go through, and we're going to write a little narrative about specifically the types of things that they agree with, don't agree with, and what they want to see people, or how they want to see people engaging in their community. But for me, this was not part of my research, but I kept seeing it, and I think it's sort of the duty of social scientists that when you see a problem coming up, you need to sort of address it. It'd be much easier if I didn't, but anyway, that's sort of where we're at there. Next steps, analyzing my data using in vivo. Thematic analysis is sort of what it's famous for. I'm going to be distributing a survey for academics working in Pond Inlet, might be expanded to just a little bit more of working with Indigenous communities, because we've gotten sort of the community's perspective, we need the scientific perspective. Carrying out the ethics work. I'm going to be going back to Pond Inlet to validate the results of the study. Very important, the community talked about. It's one thing for you to write down what we're saying, but we need to validate what we've said because there is sometimes loss of translation. And then write up and finish, 3 weeks after I get back. I'm sure I'll be done. And then the last thing is sort of comic relief, lessons from the field I wanted to tell you about. I landed in Pond Inlet. I was freezing because I had a pair of jeans on. I didn't think it was that cold. And my friends that picked me up, this is Shelley Elvram and this is Ina, said, just be careful, never leave your phone unattended. I was like, yeah. Well, it turns out you don't do that because they take selfies with your phone when you leave the room. Be prepared to walk a lot. Feel free to accept skidoo rides. Pack for cold weather and add more to it. I've lived in northern climates most of my life, and I thought I was prepared. We went out on the sea ice one day. At one point, I was welcoming death because it just hurt so bad. And they were laughing at me and told me to dance around to stay warm. I think they were just laughing at me and all that stuff. And anyway, be yourself and have fun was really the last thing I wanted to say. I wanted to say thank you, Kwana, to Hamlet of Pond Inlet, NSTP, University of Calgary, Vice President of Research's Office, Arctic Institute, my supervisor, Mary Beth Murray. Budget Rent-A-Car gave me money. There's no budget Rent-A-Car, I don't think, even in Nunavut, but thank you very much. Environment and Climate Change Canada, and SHIRT. Thank you very much.